Okay, we're live. So, all we're going to do out of chapter 8 is what's called torque. I'm sure you guys have heard of it. So, torque, the symbol we're going to use for it is the Greek letter tau, so it's like the weird looking T. So that's one of the letters in the Greek alphabet. That's what, if you ever see a T in any type of engineering or anything, it's always going to refer to that torque if you see that tau letter, okay? So torque is the only angular quantity we're going to look at this year, unless we have a little bit of extra time before Christmas, which we might. I'm thinking we might. Then we'll come back and look at some moments of inertia and do a little bit more in-depth on angular stuff. But it applies to situations where force is applied at an angle. I don't just mean like straight at an angle. We've done things like that, right? I mean like constantly curling, wrapping around. That's what a torque is. It's like a constantly curling force. And it's not just a force, it's a force through a distance. So its closest analog, its closest other type of quantity we've studied is, what else is force through a distance in a linear fashion? Force through distance is work. Okay, so this is kind of like angular work. So work that's kind of done in a twisting, curling motion. That's what torque is. We're going to have lots of twisting, curling stuff this year. But you guys should be thankful that this is the only angular quantity we're studying, because angular momentum, remember how I said there's other conservation laws, like energy is conserved, momentum is conserved. Well, angular momentum is also conserved. Angular momentum is kind of a pain to work with, so we should kind of be grateful we're kind of missing this on the first pass. It's my least favorite physics thing. It's also very confusing. So we'll maybe come back and pick a little bit more up if we have time. If not, it's not the AP exam. The only thing on the AP exam is torque, okay? So torque, I wanted us to consider like a door, and we'll go over to the door and maybe do an experiment here in just a second and see what happens. So if you'd like to volunteer, you can. So this is the hinge, this is the door in green, all right? So I want to consider two different situations. What if we apply the force like this to open the door, and what if we apply the force like that? How much torque are we creating in each situation? So torque is equal to, does anybody know? It's not very hard. It's just like that little demo you were thinking about a second ago. It depends on a radius. In other words, how far from the pin or the hinge or whatever is the force being applied. So it's radius, and the only thing that's going to produce a torque is a perpendicular force. Okay? So if you apply F1, you're going to create a large torque. If you apply F2, do you think the torque is going to be larger or smaller? Let's say they're the same magnitude, like, I don't know, 20 newtons for both of them. It's going to be less torque, right? So if you tried to open the door this way, and there's someone on the other side that you've got to push through, you're going to have to push a certain amount to open the door, right? If you try to open the door like using the edge, and you're still going to be able to open the door, except you're going to have to apply a lot more force probably, and that depends on what? Depends on what angle you apply that at, okay? So we want to be able to consider all those situations, because sometimes the force isn't perfectly perpendicular, right? Like all kinds of situations, it's not going to be perfectly perpendicular. So what if it's not? In that case, you need to just simplify this. And you can use sine or cosine of theta. You need to draw a picture so you're clear. So like we have a picture here, let's pretend we have, let's just erase, let's pretend we have a force like this one, okay? So in that case, and let's say it's applied at like this angle. So I can say 30 degrees, 60 degrees, whatever. My personal way to handle this would be to translate that vector. Vectors are the same if you move them, are they not? Translate it up there and think about, you really just want the perpendicular component, do you not? So in this case, is that a y or an x component? Y, it's this, right? This is what I really am searching for, that component, which is the y component, so this is that angle, right? So in that case, if you have something like this, I'd write magnitude of the force, maybe something like that, right? times what? Sine of theta. That's how I'd get just that vertical part. Now sometimes in your problems, and we'll see one in just a second, you might use a cosine of theta, but it all depends on how your drawing looks, right? You need to be, he is perpendicular to the, this is what's called the lever arm, okay? You have to be, to get a torque, you have to be only thinking about the force that's perpendicular to that lever arm. So if we have a lever arm that looks like this, maybe we might use a cosine because we're like going out that way or something. Okay, we'll see one just like that in a second. So do you guys believe me, or should we go try to open the door with different pushing powers?
Yeah, I want to see how you open the door with this.
Let's do it in a second. Let's do it at the end of class. So, yeah, well, hang on. Units wise, what are the units going to be for torque? If it's a distance times a force, what's that going to be? SI units? Ah. What's distance? What's force? Newtons. So it's a Newton meter.
Oh my God.
Okay, English. Let's just recall what English is, because I doubt you hear this on products that have torques on them, like a lawnmower or anything.
These days.
What is the English unit of force?
Pounds.
So the force part is the pound, and English and distance is feet. You guys heard that, foot pounds? So whenever you hear foot pounds, that is a unit of torque, right? So that's that angular quantity torque. Okay? Let's look at the book. Let's look at two examples. Okay, 8.8. Have a look at 8.8, and then we'll talk about it. Oh, I need mine. Darn it. Okay, so 8.8 says, with your bicep muscle. Let's just think about this. We're supposed to consider two things. It says the bicep muscle exerts a vertical force on the lower arm. For each case, calculate the torque about the axis of rotation at the elbow joint, assuming the muscle is attached as it's shown. So what do you guys think? Is there going to be more torque when you're perfectly like this at a 90-degree angle? Is there going to be more torque if you're holding something heavy up, like a book? Or is there going to be more torque when I go down like that a little bit? Which one is going to require more effort?
90. When it's not 90.
Only 90.
It's a tough question, right? I think effort isn't torque, right? But technically, if you hold something down like this a little bit, it's a little bit easier. So I think there's going to be a little bit less torque on your muscle. There's some other things involved too, but there's going to be a little bit less torque on your muscle here compared to here. So that's what we're thinking is going to happen. Let's calculate it and see if it matches. Okay. So let's see. The first one is just perpendicular, isn't it? That one should be easy. So what's the torque when they're like that? It's just going to be R times the perpendicular force. So what are we going to have?
0.05 meters.
So they said, why'd you get 0.05 meters, Paul?
Because centimeters and meters.
It's 5 centimeters. And how do you know that's the lever arm?
I looked at
So that's kind of like what the picture has, right? It has like R like that, and then the force is being exerted straight up. So it looks like it's perpendicular, so we don't have to worry about any angles. We just put the force in. Did they give us a force?
700 newtons.
They said 700 newtons to hold up whatever this thing is holding. Maybe it's a book, I don't know. That sounds like a bit much for a book, doesn't it?
Car.
It's a little heavy. I don't know. Maybe this is like a 50-pound weight, something like that. Let's guess. 50 times. How would we get the weight? How would we get that newtons? 50 times
4.4.
That'd be 500, so it's about a 70-pound weight. Ooh,
Or 70.
It's gonna produce some
70
torque.
kilogram.
70 kilograms. Very good. Very good.
Good. Turned out okay.
Okay, so that's if it's like that. What do they say? What do they say happens in part B? So that's the really interesting part. Part B says what happens. It says you've got the force is still going up like this, right? There's the force. And then you've kind of got the situation that looks like this. The arm is bent, and you have like that 5 centimeter piece goes like this, right? So like here's your arm as it's bent. They said to bend it, what, 30 degrees or something? So we need to somehow think about this so that it's perpendicular, okay? There's different ways, and the book says that there's 2 ways to do it. My personal preference is, hey, why don't we just make this the lever arm so that now it's perpendicular? What do you guys think? When you have this part, is this part going to be shorter or longer than 5?
Shorter.
It's going to be shorter. Now this, they said make that a 30-degree angle. So this is going to be like our new, I guess I shouldn't use the same color. This is going to be like our new lever arm. Okay? So our torque is going to still be like R, or the lever arm, times the perpendicular force. So I don't think we're going to have to mess with the force, it's just we're thinking about the lever arm a different way. There's another way to do it too, which we can look at if you guys want. But I think it's easier to do that. So if we just want that, how should I get that? It's cosine, isn't it? If you just want this part, and you've got 30 and you've got 5, and then you go the magnitude 5 times the cosine of 30. That part's going to be the lever arm, and then my force is still whatever it was before. I guess I just read still. It's still 700 newtons. So what does that turn into? 5 cosine 30, let's see.
0.05.
Ah! 5 centimeters, 0.05, you're right. So it's going to be a little bit shorter, I got that much. Times 700, just going to give me a little bit less torque. So I got, it was about, significant figures wise, that many Newton meters. So up here I should have had, I had 35 Newton meters. So it is a little bit less, not a whole bunch of difference, but that's only when you go down 30 degrees. If you drop it more, it's probably going to be a lot less. Okay? So let's look at the book. Look at what they did. So look at C. You guys see C off to the side? C is kind of what I did. Have a look at C. You see how it says R perp there? R with the little perpendicular thing? That's what we did. We found the lever arm and then left the force alone. What's the other way you could do it? Look at D. D says, hey, why don't you just consider this force not being right there? So you've still got the same situation. Here's the arm, right? Consider that force being applied right here. Here's the force. And then what else did they do? They said, okay, this is 60 degrees, right? That was 30 degrees. And what did they do? Have a look.
Perpendicular to the arm.
Here's the lever arm, right? And how'd they do the perpendicular thing? They went out like this, right? That's F perp. So I think that's a little bit harder to think about that way. So then how would that go if you just want that way? So you say, what would you do? Wouldn't you just go like this is 0.05, and then you'd go what to get the green force? It's not 700 anymore, is it?
Can you
Draw this triangle.
Because the force.
Yeah. So this triangle has 700 right here.
I think you drew that a little bit wrong.
I don't think so.
No, the dotted line is perpendicular to the perpendicular force, isn't it?
Right here?
question to be perpendicular to the green one.
Oh, right.
Yeah. Yeah, like that.
My bad. See how it gets confusing if you do it this way? I like the other way better.
No, it's.
The key is that this thing is shorter than the red thing, so you're still going to get something smaller, and you use the sine of 60, right? So you could use the sine of 60, or you could go over here and say, make that 30. Are you guys okay with this? You can make that 30, and then say in this triangle, you can use cosine of 30. So it's kind of up to you, but just make sure you've got a perpendicular thing that you're considering. That's all I want to say. Be careful about that. The next example, I think, will make that a little more clear. So this was kind of tricky, I think. A little bit tricky. Let's look at the next one. So last thing for today, 8-9. So 8-9 says you've got like two, maybe they're gears or something, and they're inside of each other. And they're rotating according to different forces. So there's two forces that were applied. Doesn't mean there just has to be two. I think one of your problems has like 3 in the homework, and I think I'll probably put one something like this on the test. I could put 5 forces on there. It doesn't matter how many. So we've got 2 different radiuses, and we apply a force right here. Okay, so we're going to kind of spin that one down that way by going, and then we're going to apply another force up here, not perfectly perpendicular, but kind of like that. So that one's going to be kind of rotating which way? The outside one is rotating clockwise, and the inside one is rotating counterclockwise. How fast are they rotating? Well, we don't really know. Depends on the size of those. So I'm going to say this one is 50 newtons. That's that force. Okay, let's call that force A. And then this one we'll say force B. I think we say the same 50 newtons there, except this one is applied at a bit of an angle. Let's say that's 30 degrees. Okay, so the question is, what is the torque overall? So I think first we should probably define a direction as positive, right? Since there's 2 directions, we should define one as positive. I think I'm going to go this one. I don't think it really matters, right? Like, why did I pick that one? And why did the book pick that one? Which one of these do you... It's going to be the
More force.
Aren't you going to get more torque from this one than from that one? Because this one's completely
Perpendicular.
and this one is
But it's got a larger radius.
not completely. Maybe the radius will kind of compensate though, so I don't know. Good question, Paul. Very good. That's true. But we're guessing that, so it really doesn't matter. So that way's positive. So the torque is going to be like thing A, and then since this is going backwards, plus or minus torque B. Okay, so that's the idea. So I need to tell you the radii, right? So there's radius A, there's radius B. I think the book said they were certain things, right?
30.
So radius A was 30 centimeters, and radius B is 50. Okay, then I think we should be set. So A is easy because it's perpendicular. How much torque are we going to get?
50 times 0.3.
RF.
For A?
30 times.
3 times 50. You had it, Paul. I'm sorry. I was looking at the other 50. 50 centimeters. And then for torque B, we've got to be a little bit more careful because we've got an angle. So let's just think about, once again, just draw it and you won't have an issue. You want the perpendicular part of that. Which part of that is going to be perpendicular? Here's the radius.
Side 30.
So we really just want, I didn't draw it very well, but isn't this part right here really going to be the perpendicular part? I guess I should draw it better. So. Does that make sense?
Yeah.
That makes a little more sense. So now it's actually perpendicular, so you really just want the x component, which is the cosine. Okay. So you'd go over here and say, all right, for that part right there, I just want my 50 newtons, that's the force, times the cosine of 30 times, how long is my lever arm? 0.5. Okay? That's it. So we've got negative 6.7, that turns out to me, and units, help me? In meters, we just learned that. So that's how much torque. So which way is this thing rotating?
To the right.
Clockwise.
Clockwise, right? So your comment, Paul, turned out to be correct. We were thinking that maybe this guy would make it end up rotating this way when you applied both forces, but since this one was applied out of the edge a farther distance, that kind of overwhelmed it. So that's the power of torque. The farther away you do something, the more torque you actually get. That's why mechanics use wrenches that are as long as possible, right? As long as they can grab, there's longer is better. You get more torque. Okay, so that's kind of strange, but
Longer.